Okay, in this lecture, we're going to cover the second part of our section 1.3 material on polar coordinates. And in this part of our lecture, we're going to talk about polar equations and the graphs of polar equations, which would give us something called a polar curve. So we know, of course, in the rectangular coordinate system, if we have some equation of the form y equals f of x, we can graph that function and we create a curve in the Cartesian plane. So in a similar way, we can graph what's called a polar curve, which would be a curve generated by a function of the form r equals f of theta. So we have an equation, instead of involving the rectangular coordinates x and y, it involves r and theta. And the graphs of these sort of polar equations are called polar curves. So in this section, we'll look at a few common polar curves and what their graphs look like. So for some easy ones, let's consider the following example. We are asked here to sketch the polar curve defined by each equation. And in part A, we have the equation theta equals a constant, 3 pi over 4. So this is one of the easier types of graphs of a polar curve. We have a constant value of theta. So let's think about what sort of curve this would describe. So we have in the real plane, shown here, defined by the xy axes. So if we have a constant value of theta, let's say theta is 3 pi over 4, that means that we would be rotating from the polar axis, or the positive x-axis, counterclockwise by 3 pi over 4 radians. And we would be looking at the set of all points of the form r theta that satisfy this equation. So we're looking for points in the plane that have this angle measure 3 pi over 4. So if we allow r to range through all positive values, that means along this line determined by that angle, r could take any positive value. So we're allowed to extend infinitely far along that line defined by this angle measure. And as r would increase, we would be tracing out this part of our line. But we also mentioned, well, polar coordinates don't necessarily have to have a positive r value. We could have a negative value of r by extending in the opposite direction determined by our angle. So here, if we take all negative values of r, we would see points along this part of our line. So what we find is that the graph of a polar equation that's given by a constant value of theta is a line. So here we have the following equation defining our line. This is also, we can recognize as the line equals y equals negative x, if we were to use the Cartesian coordinate system. So let's look at another one. In part B, we have a polar equation which is defined by a constant value of r, namely r is equal to 3. So let's think about what sort of curve that describes. So again, in the real plane, we can have our xy axes. And if we're talking about a constant value of r equals 3, let's think about what that defines. So that means that from the origin, or the pole, we can move outward 3 units. And then, since there is no restriction involving theta from our equation, it only involves r, that means that the angle that we can rotate by could range among all values. So that is, we could rotate around a full circle or multiple times around this circle. And what we would be tracing out is a circle, in particular a circle centered at the origin of radius r equals 3. And as theta ranges through all real values, we would continue to orbit around this circle infinitely. And so we see here that a constant value of r defines a circle of indicated radius, whatever the value of r is. So let's look at another one. In part C, we have a linear equation in terms of r and theta. It's r is 1 plus 2 theta. And we're specifying that theta, the angle measure, has to be non-negative, greater than or equal to 0. So let's think about what sort of curve this type of equation describes. So in our xy plane, let's start by considering the starting value of theta that we're given. So we know that the smallest value theta can be is 0. So if theta is 0, our equation says that r is equal to 1. So if we do not rotate by any angle, we would be moving outward along the polar axis, or the positive x-axis, a distance of 1 unit. And now as theta starts to increase, that is, as we start to rotate in the counterclockwise direction, we see that the value of r, which is 1 plus 2 theta, would also be increasing. So as I start to rotate in the counterclockwise direction, my value for theta, my value for r will also be increasing, and it continues increasing in this outward direction. So we see a spiral emerge. So here, since we were specifying that theta is non-negative, we see that we were spiraling outward in a counterclockwise direction. If theta was allowed to be negative, or only negative values, we would have a spiral in the clockwise direction. Okay. So we see in this first example how to graph some simple polar equations, a constant value for theta, a constant value for r, and we see here that a linear function in terms of r, so r as a linear function of theta, produces a spiral. And whether theta is positive or negative determines the direction of that spiral. Okay. So let's look at some other polar equations, which would be a little trickier to graph, and see how we might try to graph these. So one approach that we can try to use for graphing polar curves is to transform the polar equation into a Cartesian equation, and then we might recognize that equation as the graph of some known curve. So to illustrate this, we'll look at a few examples. So here we are asked to, for the given equation, find a Cartesian equation for the same curve, which is given by the polar equation, and then identify what that curve would be. So we want to describe our curve. So in part A, we have the polar equation r equals 2 sine theta. So let's think about what this looks like, or how we could obtain a Cartesian equation. So we know from our conversion formulas in the first part of this section that the Cartesian coordinates for a point x and y are related to the polar coordinates by the equation x equals r cosine of theta, y equals r sine of theta, and the polar coordinates are defined by r equals the square root of x squared plus y squared, and theta satisfies tangent of theta is equal to y over x. So let's make use of those conversion formulas to transform our Cartesian or our polar equation into a Cartesian one. So looking at part A, we have r equals 2 sine theta. So if I want to get something that looks like one of our formulas for converting between these coordinate systems, well, I see that the right-hand side involves a sine theta. And I know that if I have r times sine of theta, that's just equal to y. So in order to get an r in front of the sine theta term on the right-hand side of our equation, we can multiply both sides of this equation by r, and we would have r squared is equal to 2r sine of theta. So let's see if we can make the conversion to a Cartesian equation now. So on the left-hand side of this new equation, we have r squared. Now we know that r is equal to the square root of x squared plus y squared. So r squared is then just the sum of x squared and y squared. Now on the right-hand side, we had a constant 2, and then the term r sine of theta, we know from our conversion formulas, is just equal to y. So we have x squared plus y squared is equal to 2y. So let's think about what type of curve this equation describes. I claim that it's a circle, but in order to see that, we might want to rewrite this equation in the form, or the standard form for the equation of a circle. So in order to do that, I'm going to move all of my variables to one side of our equation. So I have x squared plus y squared minus 2y is 0. And now I'm going to group the variables x and y together and complete the square in both quadratics. So the only term I have involving x is this x squared. And if I group the y terms together, I would have y squared minus 2y, and this is equal to 0. So my goal now is to complete the square in each of these quadratics. That is the quadratic involving the variable x and the quadratic involving y. Now the x terms are already a complete square. We just have x squared, or x minus 0 squared. And in order to complete the square in the variable y, well, I have y squared minus 2y. And what I'm looking to do is add some constant term such that my quadratic can be factored as a perfect square. So you might recall in general, the term that you want to add is the square of half of the b coefficient. So when I'm saying the b coefficient, remember in general quadratics can be written in the form ax squared plus bx plus c. So we're going to take half of our b coefficient, in this case half of negative 2 would be negative 1, and then I'm going to square that value, which would give me a positive 1, and that's the constant term that I want to add on the end. Now, of course, if I add a 1 on this left-hand side of my equation, I must also add a 1 on the right-hand side of the equation so that this equation is still true. Now let's take a look at what this buys us. We now have an equation of the form x squared plus y squared minus 2y plus 1, which factors as y minus 1 quantity squared, is equal to 1. So what we have now is a Cartesian equation describing our curve. This is what we wanted. And we recognize this as the standard form for the equation of a circle. So the graph of this polar equation is a circle, and we can describe this in a little more detail. The center of this circle would be the point 0, 1, and the radius is 1. We can see from the right-hand side of our equation. All right. So let's look at another one somewhat similar. In part B, we have r equals 9 cosine theta. So sort of following the work that we had done in our part A example, let's maybe start by multiplying both sides of the equation by r. Now, why do we do that? Well, this right-hand side of our equation involved a cosine of theta. So if I multiply by r, I now have r cosine of theta, which we know is equal to x. And on the left-hand side of our equation, we have r squared, which in terms of Cartesian coordinates is x squared plus y squared. So this equation is now x squared plus y squared is equal to 9x. So we now have a Cartesian equation. We want to describe the graph of it. And again, I claim that this is a circle, but to see that it is indeed a circle, we need to manipulate this equation and write it in standard form. So as we did in part A, let me start by moving all of my variables to one side, maybe the left-hand side, and I'm going to group the x and y terms together. So here I have an x squared minus 9x, and then a plus y squared. So as we did in part A, I want to complete the square in each quadratic. Now y squared is already a perfect square. We just need to complete the square for the x quadratic. So as we did in part A, we're going to add some term to x squared minus 9x so that it can be factored as a perfect square. Now again, the constant term that we want to add is found by taking half of this b coefficient and squaring it. So here we have negative 9. Half of that would be negative 9 halves. And then squaring that, we would have a positive 81 over 4. And then I still have my plus y squared. Now, since I added an 81 over 4 on the left-hand side, I also have to add an 81 over 4 on the right-hand side. And what this allows me to do is now factor the x quadratic as x minus 9 halves quantity squared plus y squared is equal to 81 fourths, and this is now in the standard form for the equation of a circle. So again, this equation is defining a circle, in this case with a center of 9 halves 0 and of radius 9 halves here. Okay. So let's look at another one. In part C, we have r equals a constant times cosine theta minus another constant times sine theta. So if we follow the same sort of approach that we did in parts A and B, I realize that if I multiply both sides of this equation by r, I get the r cosine and r sine theta terms on the right-hand side that I recognize from my conversion formulas. So the r squared on the left-hand side of the equation in Cartesian coordinates is given by x squared plus y squared. that is equal to 6, and then r cosine of theta is equal to x. We have a minus 8, and the r sine theta is y. So again, we have our Cartesian equation, and I claim that this represents a circle. But again, in order to see it, we would need to group our variables and complete the square in order to write it in the standard form for the equation of a circle. So moving all of my variables to the left-hand side and grouping our x and y terms together, I would have x squared minus 6x, and then plus a y squared plus 8y is equal to 0. And now I'm going to complete the square in both of my quadratics, that is the quadratic with respect to x and with respect to y, and see that we have a equation of a circle. So the constant that I would need to add to the x quadratic is found by taking half of the b coefficient, so negative 3, and then squaring that, which would give me a positive 9. And the constant that I would add to the y quadratic, y squared plus 8y, is found by taking half of this b coefficient, so half of 8 is 4, and then I square that to get a 16, and that's what I'm adding. Now this is equal to, let's see what we have. So on the left-hand side of my equation, I've added a 9 to the x quadratic and a 16 to the y quadratic. So in total, I've added 25 to the left-hand side, so I must also add 25 on the right-hand side in order to keep this equation valid. Now from here, we can finally factor as x minus 3 quantity squared plus y plus 4 quantity squared is equal to 25. And this we recognize as the standard form for the equation of a circle. This circle would have its center at the point positive 3, negative 4. And it has a radius of 5. Since our right-hand side was 25, then the radius is the square root of that value, in this case 5. So we see these first few examples where we have r is equal to some constant multiple of sine theta or cosine theta, typically represent circles. And to determine the center and radius of the circle, we can transform that polar equation to a Cartesian equation and then write it in the standard form for the equation of a circle. So let's look at some other ones. In part D, we have r is equal to 5 secant theta. Now, we see that we are now involving the trig function secant theta, and our conversion formulas all involve either sine, cosine, or tangent theta. So my goal here might be to first rewrite the secant theta term, 5 secant theta, in terms of sine or cosine. Now we know that secant theta is the same as 1 over cosine, so really we have r is equal to 5 cosine theta. And then if I multiply both sides of this equation by cosine theta, I have an r cosine theta is equal to 5. But at this stage, we recognize the left-hand side, r cosine theta, as simply being x in terms of rectangular coordinates. So the equation given here is the same as the Cartesian equation, x equals 5. So the graph of a constant value of x would be a vertical line, in this case passing through the value x equals 5. So let's look at another one. In part E, we have the equation r is equal to secant theta tangent theta. So as we did with the previous example, let's rewrite those somewhat messy trig functions, secant and tangent, in terms of the more familiar trig functions sine and cosine. So I have here r is equal to secant theta, which is the same as 1 over cosine theta. And then tangent of theta can be rewritten as sine theta over cosine theta. So we now have r is equal to, multiplying our fractions, we have a sine of theta over cosine squared theta. And in order to eliminate the fractions here, I'm going to multiply both sides of my equation by cosine squared theta. So what I now have is a polar equation equivalent to the one we started with, of the form r cosine squared theta is equal to sine theta. Now if I want to convert to a Cartesian equation, I'm going to need to make use of my conversion formulas. So as we saw in our previous examples, on this right-hand side where we just have sine of theta by itself, we could multiply both sides by r in order to get the conversion formula r sine theta. So multiplying through by an r, the left-hand side is r squared cosine squared theta, and the right-hand side is r sine of theta. Now, of course, this left-hand side, r squared times cosine squared theta, can be rewritten as simply r times cosine of theta quantity squared, which is equal to r sine theta. And now we can make use of our conversion formulas. So we recall that r cosine theta is equal to x, and r sine of theta is equal to y. So this equation becomes x squared is equal to y, or y equals x squared, which we recognize as describing a parabola with vertex at the origin and opening upward. So this example illustrates how we can convert a polar equation into a Cartesian equation. In some special cases, it's not always possible to do this. And if we are able to obtain a Cartesian equation from that polar equation, we can then graph it a little more easily using what we know about graphing in terms of Cartesian coordinates. So let's look at some special types of polar equations which give polar curves that appear fairly frequently. We'll see them a lot throughout this course. So these curves are given special names. So we'll see first how to sketch these curves by hand, and then we'll take a look at some software that we can use to sketch high quality graphs of these polar equations. So the first special type of curve that we're going to talk about is known as a cardioid. And so what sort of polar equation describes a cardioid? Well, it would be a polar equation of the form r is equal to a, some constant, times 1 plus or minus sine theta, or an equation of the form r is equal to a constant a times 1 plus or minus cosine theta. So the graph of such an equation is called a cardioid, and the reason for the name, as we'll see in just a moment, is that these cardioids are shaped somewhat like hearts. So let's look at the graph of a couple of these, first by hand, and then we'll look at some software that we can use to get a little better figure. So here we are asked to sketch the graph of the given polar equation. And in A, we have r is equal to 1 plus cosine theta. So one way that we might try to graph this is by converting to Cartesian coordinates, as we did in our previous examples, but we see that it gets a little bit tricky here. So if we try to do that with our equation, we might try to multiply both sides of this equation by r, as we did earlier. So we would have r squared is equal to r plus r cosine theta, and we know that r squared is simply x squared plus y squared. Now r, we're still stuck with, and then we have a plus r cosine of theta, which is equal to x. So the tricky part here is that I get stuck with this factor r. Now, if we make use of the fact that r is equal, or x is equal to r cosine of theta, we could solve for r in terms of x as arc cosine of or well, let's see, no, we can't even get that here. So we get stuck with this r term, which is not very, does not give us a nice Cartesian equation very easily, certainly not one that we know the graph of. So let's think about what else we could do if we cannot convert to a Cartesian equation. So we can always plot polar curves by finding points satisfied by this equation, and then plotting those points in the polar plane and then connecting the dots, sort of the same way that you initially learned how to plot functions in Cartesian coordinates. So let's start by instead making a table of r and theta values, which would satisfy this equation, and plot our points. So here, r is defined as a function of theta. So let's make a little table of theta and r values. So I'm going to start with theta as being equal to 0, and I'm going to increase theta in increments of pi over 2. So I'll go from 0 to pi over 2, then up to pi, then up to 3 pi over 2, and then to 2 pi. So we're going to look at what this curve looks like as we revolve from 0 to 2 pi. That is, as we make one full revolution from the polar axis. So looking at our equation, r is equal to 1 plus cosine of theta. So if theta is 0, then r would be 2. Now, if theta is equal to pi over 2, we would have r is equal to 1 plus cosine of pi over 2. Now, cosine of pi over 2 is 0, so r would be 1. When theta is equal to pi, we would have r is equal to 1 plus cosine of pi. Now, cosine of pi is negative 1, so we would be left with r equals to 0. And then when we increase theta to 3 pi over 2, we would have 1 plus cosine of 3 pi over 2, which is 0. So we're just left with the 1. And then as theta increases to 2 pi, r is then 1 plus cosine of 2 pi. That's the same as cosine of 0. So we get back to r equals 2. So once we have these points, let's plot these points in the polar plane, and then we'll connect our dots to see what this curve looks like, at least a rough sketch. So here we started with the point where r and theta are 2 and 0. So that means when theta is 0, when I haven't rotated from the x-axis, I'm going to move outward from the origin 2 units. So I have this point in polar coordinates 2, 0. Now, as theta increases to pi over 2, that is, as I've rotated by pi over 2 radians to the positive y-axis, r was equal to 1. So along that positive y-axis, I'm going to move from the origin 1 unit outward. Now, as we continue to increase theta, that is, as we continue to rotate up to theta equals pi, we had an r value of 0, which means that we do not move outward along that negative x-axis, but rather we are staying at the origin for that point. Again, as we continue to rotate to 3 pi over 2 radians, which gives us the negative x-axis, or excuse me, negative y-axis, we found that r is equal to 1, so we're going to move from the origin 1 unit outward along the negative y-axis. And then as theta increases to 2 pi as we make our full rotation back, r again is 2. So let me clean up my figure a little bit here to just show the points that we've plotted. So these 4. Now, if we want to get a little better idea of what the graph looks like, we can choose theta values between 0 and pi over 2, say pi over 4, and find the corresponding r value. And what we get when we do this is a curve that looks something like the following. So we were starting at the point 2, 0, and as theta increases, we have a curve that passes through the points in this indicated shape. And as we continue to revolve, we see that our curve traces out the following path. So the graph of this curve is sort of this heart shape that we see here, and it's called a cardioid. So, of course, if we only use the 4 points, which we had shown here, it might be a little difficult to see that our curve has that shape. So instead of sketching by hand, we can always make use of software to sketch these polar curves. So I'll show you here. Let me go into my browser. One way to plot these polar curves, which is available to you for free. It's again going to make use of that Desmos site that we use to plot parametric equations. So here, in order to find this tool, you can go to your favorite search engine, search for Desmos polar plot, and it should be the first link that pops up here. So here there's this first link called polar coordinates dash Desmos. If I click on that link, it will bring up the following graphing utility. So the way that this will work is in the right-hand side of our screen here, it's showing the polar plane along with the XY axis over it. So we see these different circles of various radii moving outwards, and we're going to plot our polar equation in red. So this left-hand box where you see these different equations for r specified, you're going to edit this first equation. So here, the default one is given as r is 3 minus 3 cosine theta, which we can see in red in our graph. It is also a cardioid. Now, the one that we were plotting was 1 plus cosine of theta. So let's edit this just a little bit. So to edit, you can make use of your keyboard to redefine r. So we have currently shown as the graph of r equals cosine of theta, which we see as this little circle shown in red. And then if we want to change our equation to what we were given, which was 1 plus cosine theta, we can input that. And then we can define a range of theta values. In this case, we were looking at the interval from theta is 0 to 2 pi. So we're tracing out this full cardioid, which was shown in red in our figure there. So we see it looks similar to what we had sketched by hand, but of course it's a much nicer looking graph. So let's look at another one. In part B, we have r is equal to 1 minus sine of theta. And if we try to convert to Cartesian coordinates, it doesn't work out very nicely. So instead, we can make use of a table of values for theta and r given by this equation, and then plot those points and connect our dots. So again, I'm going to take values of theta from 0 to 2 pi, spacing them apart by pi over 2 units. Now you can take more points that are spaced out not as far apart if you wish to get a few more points on the curve and sketch this more precisely. But since we have that graphing utility available to us, it's really not necessary here. So let's find the corresponding r values. So r was given by 1 minus sine theta. So if theta is 0, r is 1. If theta is pi over 2, r is 0. If theta is pi, r is 1. If theta is 3 pi over 2, we would have 1 minus sine of 3 pi over 2, which is negative 1. So 1 minus that negative 1 gives us an r value of 2. And then if theta is equal to 2 pi, we're back to r equals 1. So let's plot these points. Starting with theta equals 0, we had an r value of 1. So if we don't rotate at all from the positive x-axis, we're moving from the origin 1 unit outward. Now our next point, when we rotate by pi over 2 radians, we're looking at the positive y-axis, and we have r equals 0. So we don't move outward from the origin at all along that positive y-axis. Now as we increase to theta equals pi, that is if we rotate to the negative x-axis, r is 1, so we're moving 1 unit outward from the origin along that negative x-axis. When theta is 3 pi over 2, so we're rotated down to the negative y-axis, and r was 2, so we're going to move from the origin 2 units outward along the negative y-axis. And then when theta is equal to 2 pi, r is 1. So we get back to the same point that we started with. Now if we were to use more values for theta and get more points, we could connect those dots and we would see that our curve looks something like the following. So again, it has kind of this heart shape, which is why these curves are called cardioids. And we see here that it's sort of extending downward from the origin along that negative y-axis. In part A, we were moving from the origin, kind of extending along the positive x-axis. So let's take a look at this same curve plotted using Desmos. We had r is 1 minus sine theta. So going back to our graphing utility, we could change our equation for r to be 1 minus, and then to input sine theta, we would go to our functions button. And we have sine of the variable theta. Let's see if we can find that here. So if you go to your keyboard, we see a theta variable here and just underneath p. So inputting that, we have the following. Closing our parentheses, we can see that the graph updates accordingly. We have that cardioid shape graphed much more nicely here than what we did by hand. Okay. So another type of familiar curve, which will show up throughout the course, is a rose curve. So we can see that these curves are called rose curves by looking at some of the graphs that I've illustrated below. They have sort of a flower shape, or like a rose with a certain number of petals. So when do these curves arise? Well, we would have the graph of a polar equation of the form r is equal to a sine of k times theta, or r is a times cosine of k times theta. where a and k are both constants. So the graph of these curves are called Rose curves. And in general, the number of petals is determined by the constant k. So in particular, if k is odd, then our rose curve would have k petals, or leaves. And if k is even, then our rose curve has 2 times k petals. So when k is odd, you have as many petals as you have for the value of k. If k is even, you have 2 times as many petals as that value k. So to illustrate this, there's a couple of cases. We have the first case, case 1. If we're looking at the graph of an equation of the form r is a sine of k theta, so if it involves the sine function specifically. So we've shown here a rose curve sketch for k equals to 3. So we have a rose curve with 3 petals, or if k is equal to 6, which is even, we would have twice as many petals. We see a total of 12 here. Now our second case, case 2, is the case where we have an equation of the form r is a times cosine of k theta. So when we're working with cosine, we have a similar situation, but there's a slight difference, which I'll discuss in more detail shortly. So just to illustrate here, we have the case where k is 5. So since k is odd, we have 5 petals. And then the case where k is even, if k is 4, we have a total of 8 petals shown here. So the graphs of these rose curves are slightly different depending on whether you're working with the sine or cosine case. Let's think about why that would occur. So let me start by looking at the cosine case. So starting with an initial theta value of 0, well, we know that cosine of 0 is 1. So we would have an r value of a, whatever that constant is. So along the polar axis, or the positive x-axis, defined by theta equals 0, we're moving out a distance of a units. In all of the examples that I've shown here, a was chosen to be 1. And then as theta increases, we start to trace out these petals of our rose curve. So they follow this sort of path. And as theta ranges from 0 to 2 pi, we see the full rose curve. Now, what's slightly different in the case that we're working with sine of theta is that our initial petal does not open along that polar axis, because we know the polar axis defined by theta equals 0. Well, if we're graphing a sine function, r would be a times sine of 0, which is 0. So we start at the origin along that initial x-axis, or polar axis, and the initial petal will open along some angle above that positive x-axis. So this first petal is traced out at an angle above the x-axis. Whereas in the case that we have a cosine equation, that initial petal is opening along the x-axis exactly. So a slight difference in what our curves look like. So let's look at our last example here. We're asked to sketch the graph of each polar equation. And in part A, we have r is equal to cosine of 2 theta. So here we recognize this as being the equation for a rose curve. Let's think about how many petals it will have. So in this case, our value for k is 2. We had cosine of 2 theta. So since k is even, that implies that we have twice as many petals, so a total of 4 petals. And since we're graphing the cosine function specifically, that initial petal will open along the positive x-axis. Now our value of A is 1 here. We had 1 times cosine of 2 theta, so the length along any of these petals would be 1 unit. So we have, when theta is 0, a value of 1, and our initial petal of the 4 is opening along this axis. The other few are shown here. All right, so we would have a rose curve that looks something like this. Now, in part B, we have R is sine of 3 theta, which again we recognize as an equation for a rose curve. The value of A is 1. We had 1 times sine of 3 theta, so our petals will have length 1, and K is equal to 3 here. Now, since K is odd, that implies that we have exactly as many petals as the value of K, so in this case, 3 petals, and our initial value of, or the initial petal will open along an angle above that x-axis. So to find that angle, we can think about where our sine function is maximized. We know that sine of pi over 2 is equal to 1, so that would be our the tip of our petal there. Now, here our angle is sine of 3 times theta, so we would set the angle 3 theta equal to the angle where we know sine is maximized at pi over 2, and then solving for theta, we have pi over 6. So when we're rotating by pi over 6 radians, that is the angle along which that initial petal is opening. Now our other few petals are shown here. So very rough sketch, we have this little 3-petal rose curve. And of course, to get more high quality graphs, you can make use of that Desmos program. So let's take a look at this one. We had R is a sine of 3 theta. So let's take a look at how to graph this in Desmos. So we have R is sine of 3 times theta. And we can see that our graph updates accordingly in this right-hand window. We see a little 3-petal rose where that initial petal is opening along that angle determined by pi over 6 radians. So of course, for rose curves which have many petals, it's best to use this Desmos program to get a really high quality graph. And I'll mention at the end of the section, I give a note here that there are some other types of frequently used polar curves, which are given special names. And we won't go through all of these in full detail. However, there is a summary of these common polar curves, some of which we've already looked at are circles, cardioids, and rose curves. Now, a couple of other common types are known as limacons and limnoscates. These have sort of a figure 8 general shape, or something that looks like a cardioid, but maybe it has an inner and an outer loop. And a summary of these different common polar curves is given in that online textbook. So I'll mention that it's probably best if you familiarize yourself with these different types of common curves, what they look like, and what sort of polar equation yields those curves as its graph.